Okay, B, intrinsic geometry, exterior algebra, extended to R3 and R4. B, part 3, miscellaneous topics in intrinsic geometry, also extended to extrinsic geometry, as is in this case over here. So B, part 3, lecture 4, application of the Euler-Lagrange equations. Now, I would like for you to note that all these initial lectures is just to follow such that in the final we'll get the Hamiltonian written in terms of the Lie bracket. Okay, this is first lectures. It's just to go, okay, to a target. A target is the Hamiltonian, okay, expressed in terms of the Lie bracket. Now, from lecture 3A and B, 3A and 3B, of the Euler-Lagrange equations is this one. I call this equation 1. Now, conservative force and Newton's second law. This is mass times acceleration. This is equal to force. And the hypothesis, this force is conservative. Now, the V is a function only of the coordinates. I see, this is Q, okay? I abbreviate Q for Qi. Qi is I is equal 1, 2, 3 till n, okay? Coordinates. So V of Q is the potential energy, depends only on position. Why? Because this is related to the conservative force, okay? Now, this is a kinetic energy, okay, is 1/2 m. This is, again, this Q point, actually it is Q point I, okay? Then I abbreviate this for Q point only. This is the kinetic energy. Now, by inspection, we assume the Lagrangian is equal kinetic energy minus the potential energy, and the Lagrangian of the form, okay, L, function of the coordinates and velocities. So this is equal T. This is another assumption. T here is a function only of the velocity, and the force, the conservative force, is a function only of the coordinate. Okay? Now, then calculate this partial derivative over here, okay, is just m Q point I. You see, is this I component. Now, the time derivative of partial L respect to Q point I is m Q double dot here. This is the acceleration, okay? Now, partial L respect to Qi is minus partial V respect to Qi, because V is a function only of the coordinates, okay? Now, substituting into 1 over here, then leads to m, the acceleration here, plus m partial, this partial V respect to I is equal to 0. So this is from equation 1. Now, this implies that the second Newton's law, okay, m times acceleration is equal to force. It's a particular case of force. It's conservative force. So this is a Newton's second law derived by inspection. That's important. Just substituting the adequate value of L in this case, adequate value of L, okay, which is T minus V, then this leads to the Newton's second law. So, conclusion, by assuming, by inspection, I repeat, L is equal to T minus V, and apply it in the Euler-Lagrange equation, we recover the Newton's second law. This verifies that L, T minus V, is the correct Lagrangian for a conservative system in classical mechanics. You see? That's when you see written L is equal to T minus V, there are hypotheses such that I can represent the Newton's second law just using the Lagrangian L is equal to T minus V, which independent is a scalar. Attention now, this over here is a scalar equality, okay? That's important. But the Newton's second law involves is equal F is equal ma. The second Newton's second law involves in this case vectors. So when you use the Lagrangian form, you pay attention only on that. Pay attention that L is a scalar quantity. That's a great advantage, okay, for the analysis of classical mechanics. From here, I will show the Legendre identity, and then by inspection, I will write the Hamiltonian, okay? That's starting from L, from the Lagrangian. There is a correspondence, Hamiltonian and Lagrangian.